Hello everybody, this is Art and you're watching Secret Vision. This is episode 7, part 2. And the title of this episode is What the Scientists Missed and the Ice Conversion Factor. So getting down to business right away, for the first illustration, I'd like to establish the temperature boundaries on the Earth. The boundaries that affect most of the Earth's human inhabitants. There are outliers, but most of the inhabitants of the Earth live in temperature range between minus 70 and plus 110 degrees Fahrenheit. The freezing point of water resides at approximately mid-range on this scale that we just established. All right, everybody. At this time, I'm going to ask you to hang with me for a couple minutes because I'm going to go through some possibly pretty boring details about the conversion, state conversion of ice from ice to water and water to ice. And none of these things are beyond your ability to understand or grasp. And it will be important to know to understand how the vertical current transfers heat from the planet Earth to space and then brings cold from space down to the surface of the planet. So I'm calling this little segment the asymmetrical thermal exchange zone. And as I mentioned, we're going to be talking about the state conversion from ice to water. So if you have plain water and the water's at 32 degrees, it's going to require 1 British thermal unit to raise that water 1 degree Fahrenheit if it weighs 1 pound. To heat 1 pound of water from 32 degrees Fahrenheit up to 80 degrees Fahrenheit, it will require 48 BTUs. 1 BTU for every degree Fahrenheit the temperature rises. To heat 1 pound of ice, on the other hand, from 32 degrees to 80 degrees, it requires 192 BTUs. That's because of the conversion factor of ice. If the 1 pound of ice is at 32 degrees Fahrenheit, you're going to have to raise the temperature of that ice 144 BTUs just to convert it from the ice state to a liquid state, and the temperature remains at 32 degrees Fahrenheit. Then it takes another 48 degrees. So 144 and 48 degrees brings the total number of BTUs up to 192 BTUs. That is going to be 4 times as much as just converting water from 32 degrees to 80 degrees. So there is your asymmetry in a nutshell. And to try to illustrate that, it's like if the water or water vapor is above 32 degrees and you're transporting it from the Earth to the edge of space and then bringing cold from the edge of space down, well, you'd be using a pickup truck to do it. Once the water vapor gets below 32 degrees, now it's like you're transporting it up with a semi-truck and bringing it down with a semi-truck. That's the asymmetry I was talking about. We're going to do a little experiment. I'm going to describe an experiment so you know how this conversion factor will affect the atmosphere. Okay, we're at the laboratory. And in this laboratory, the ceiling area of the laboratory is a sealed chamber. And it's a chamber that's insulated so well that if you put air into this chamber and it's at minus 40 degrees, the air will probably remain at 40 degrees for hours because it can't give off any heat. Now in the core of the chamber, you have one little cylinder, and that little cylinder can hold 1 pound of water. So we're going to pump 1 pound of water at 80 degrees into that cylinder. And when the cylinder's full, the atmosphere inside the chamber is going to start absorbing BTUs from that water, pulling the temperature down. The temperature of the water will come down, but the atmosphere inside the chamber will actually rise because it's surrendering BTUs to convert that water to ice. And we already know how many BTUs it's going to surrender. It's going to surrender 192 BTUs. It's going to bring the water down to 32 degrees at a liquid state. And then to convert that water to ice, it's going to have to surrender another 144 BTUs. If it surrenders those BTUs, it gets warmer. So now our block of ice inside the little chamber is frozen solid. So we open a little trap door and the ice falls down. That's a snowflake. So the snowflake falls from this chamber, and that chamber is representing the upper atmosphere and where it has a Earth-space connection. The coolness is coming from space in the atmosphere. When the ice changes, or the water vapor changes to snow in the atmosphere, gravity causes that snowflake to fall back to the earth. The conversion factor is exactly the same. When you have 1 pound of snowflakes, the atmosphere gave up, at the very minimum, 144 BTUs, and that would be warming the atmosphere. If enough snowflakes fall, the atmosphere just continues to warm up until that heat that's left behind by the conversion of water to ice, until that heat is radiated off into the background temperature of space. The background temperature of space is at about minus 455 degrees Fahrenheit, which is just a few degrees above absolute zero. So there will be radiation from the atmosphere to space. Now that makes this current that we're talking about, this vertical current, and the current, you can see it now. Your moisture is going up, it's freezing, and it's dropping back down. So you have an upward drift and a downward drift. The difference between this current and, let's just say, the famous AMOC, or Atlantic Meridional Overturning Current, that brings water from the tropics up to the northern regions like Iceland and England, and keeps those places warm while bringing cool water from those areas down and keeping the tropics a little bit cooler. That is a closed loop system. That system, the amount of water that goes north, gets cooled down, comes down, reheats, goes back up, but it's a closed loop, and all of those BTUs remain in the earth. The current I'm talking about is a much more dangerous current. It's a current where heat rises from the earth. It surrenders heat to the atmosphere. The atmosphere warms up. The atmosphere surrenders that heat to the background temperature of space. Your snowflake was created, and your snowflake, by gravity, falls down to the earth. Now it's bringing the cold from space down to the earth. This is an open-ended system. This system, these BTUs aren't self-contained here in the earth. They're going from the earth up to the atmosphere, heating up the atmosphere, dropping back down as cold, and that cold that warmth in the atmosphere is radiating off to the space. So you have an open end at the top system. All right, we're still in the laboratory, and we're going to continue this experiment. So far, we pumped 1 pound of water into our insulated chamber, and we created one pound snowflake. So we're going to continue pumping water. The first snowflake fell. We're going to pump another pound of water up there. The atmosphere in that chamber is going to surrender more of its BTUs to convert that second pound of water to ice. So you can see as the snowfall or the ice, water in this case, converting to ice continues to fall, the chamber's going to get warmer and warmer. So in the absence of some refrigeration to bring the temperature back down, this chamber is going to warm up to the point where it can no longer convert our water to a snowflake, a 1 pound snowflake. Well, so there's an event called sudden stratospheric warming. And that sudden stratospheric warming forms over the polar region. And I'm suspicious that this conversion of ice, water to ice, and the snowfall falling away through gravity and extracting the cold out of the atmosphere, bringing the atmosphere, the cold down to the surface of the earth, and the warmth remaining up there. I'm pretty convinced that gigantic snowfalls, the kind of snowfalls that start in the west coast of the United States and travel all the way to the east coast, and similar snowfall like that in Europe and Russia and Asia, that deposited warmth in the atmosphere isn't part of the buildup of the sudden stratospheric warming. And if you see super heavy snowfall, I think the sudden stratospheric warming becomes more like predictable stratospheric warming. And there's another element that contributes. Your sun is shining light that's going to travel directly through the atmosphere to above the polar region. And then you're going to have, in coincidence with that, light that comes down and strikes the earth. The earth's turned white because of the snowfall and the snow cover, and that beam that came down hit the earth is going to reflect back up into space. So now you have over the polar region the power of 2 suns. So you have stratospheric warming coming from the conversion of water to ice, and you also have the power of 2 suns. All right, the largest contributor to cooling the planet Earth is your long-range radiation. Long-range radiation is in the lower light spectrum, and it's radiated from the Earth to the background temperature of space. We've already established that the background temperature of deep space is about minus 455 degrees Fahrenheit. So imagine your oven at 455 degrees Fahrenheit, then you open the door and the heat just radiates out. Well, that's what the Earth feels like to the background temperature of space. Even in the colder regions, if you're in the South Pole and it's minus 100 degrees Fahrenheit, that's still 355 degrees above the background temperature of space. And this is called the balance of equilibrium. Whatever heat, incident heat, is provided by the sun, the Earth is capable of re-radiating that heat back into space. So it gets hotter because the incident heat from the sun is higher. But it doesn't go out of control because it's equally capable of radiating off that same amount of heat. It would be like your car in the parking lot at the store. You go into a store for an hour or two in the summertime and you come out and the car is so hot that you can't put your arm on the windowsills and you can't hardly grab the steering wheel because it's so hot. Well, that's a perfect greenhouse, and the heat, the solar energy does heat the car up, but it's not going to heat it up to the point where it bursts into flames, because at some point, and this is something that you obviously recognize, at some point the car gets hot enough that now the car can re-radiate back into the ambient temperature that's surrounding it. If the ambient temperature's 97 degrees and the car heats up, now let's make it up 127 degrees, and it stays there. Even though it's a perfect greenhouse, it's going to stay there because it's re-radiating, and that's what the Earth is going to do. So the primary cooling of the Earth takes place by this long wave radiation leaving the Earth. But now, reinforcing the long range radiation and adding to it, now we've just discovered, well, there's a vertical current, and this vertical current is taking heat from the surface of the Earth. It's transporting it up to the upper atmosphere. It's converting to snow. That conversion process heats up the atmosphere. That snow is falling down to the Earth, and it's laying on the Earth. It's also turning the Earth white. It's reflecting incoming sunlight, and at some point when the sun starts overcoming that snow and starts melting it off, well, the 144 BTUs that it absorbed from the edge of space is now absorbing incoming heat. So it's your typical double whammy. You lost 144 BTUs converting moisture to snow. Now the snow is fallen, and the snow is going to absorb 144 BTUs of incoming sunlight. So obviously, the more snowfall there is, the more acute this becomes. So the question is, would the snow cause cooling, and then the cooling causes more snow? Are you in a downward temperature cycle now? Because you have two things radiating heat off of the Earth. You have long wave radiation, and you have a convective current that's effectively bringing heat from the Earth to the upper atmosphere, depositing it there, grabbing some of that cold, and dragging it back down to the Earth. So it's all a battle of BTUs, and it would appear that as the sun cools and the Earth receives less energy, we could very easily get into a feedback loop that is going to cause continued cooling. And so I wanted to mention the SSW and where that is a problem. So we're going to do another experiment. And the experiment is going to be, we're going to take about 3-foot round circular disc, paint it black, and put it out in the sunlight. You know that the sun is going to heat up that black surface. Well, then we're going to take and cut a hole in the center of that black surface, and we're going to drop into it a bucket of white paint filled to the top. Now that's going to represent the polar region, and anybody knows that white reflects heat, black absorbs it. So the overall temperature of this disk that we just created is going to drop down. Now this is the dangerous part of SSW. SSW dislodges some of this polar air and some of this reflectivity, and it spreads it around. It would be like you take a little air pistol and go shoot it at that paint bucket, and the paint splatters outside of the can over other portions of this black disc that we built. Well, now you still have the reflectivity. You have the initial reflectivity of the Arctic region. But combined with that, now you have white snow moving more into the southern regions. So now the overall reflectivity or albedo of the Earth is increasing. So the SSW effects, the SSW does have a cooling effect in the Earth because it's maintaining the reflectivity of the Arctic region, but it's spilling over into more southern areas. So now you have more areas that have changed color. So now the sunshine is hitting a larger surface that's turned white, and it's reflecting more of that sun power back into space. So SSW events do contribute to global cooling. All right, now we know that the Earth is primarily cooled by long-wave radiation, but during periods of a more dormant sun, we now understand that vertical currents are going to reinforce the long-wave radiation in cooling the Earth. And the vertical currents may participate in forming stratospheric warming events, and those will also reinforce the current cooling of the Earth. So you might ask, well, is there anything else? Well, actually, there is a couple things. And in episode 7, part number 3, I'm going to mention a couple things more that may involve additional cooling. So at this point, I would like to thank you for joining me. The next episode is going to be episode 7, part 3, and it's going to be called The Rhythm of the Elliptical Orbit. And until then, God bless and take care of yourself, and we'll see you for episode 7, part 3.